Okay, so as in the last video, we have discussed simple harmonic motion in very detail. And before simple harmonic motion, we have discussed periodic motion and oscillatory motion. What was periodic motion? Periodic motion was a motion which repeats itself in equal interval of time. Alright? For example, waking up early in the morning at 6 a.m. always, right? Your alarm rings always at 6 a.m. to make you wake up. So this is a periodic motion, since this motion is taking place after every interval of time, every equal interval of time. Then we discuss about oscillatory motion. Oscillatory motion is nothing but it is a periodic motion, which means oscillatory motion will also repeat itself in equal interval of time. But here we have a condition that this motion will be to and fro motion, or you can say back and forth motion. For example, we took an example of the mass spring system, where you attach a mass of a body, or you can say a body of a mass with a spring, and that spring is in, inclusive, which means it would not be stretched, right? And when you stretch it, it covers some distance from its mean position to the point, and that point is known as extreme position. Alright, so we're gonna discuss each and everything about mass spring system, but for now it was only an example of the oscillatory motion. Then we discussed about simple harmonic motion. Then we said simple harmonic motion. What's the meaning of simple harmonic motion? It is the simplest form of oscillatory motion, right? It is the simplest form of oscillatory motion, which means it would be periodic motion, which means simple harmonic motion we're going to repeat itself in equal interval of time. Secondly, it will be to and fro, back and forth motion, since it is oscillatory motion, right? The third condition is it must be straight line motion, which means if I take an example of the simple pendulum, if I move it a bit, it will gonna move to and fro or back and forth, but that too in a straight line, right? So this is what we call the simple harmonic motion. In today's video, we're gonna study the characteristics of simple harmonic motion, the conditions which you're going to apply to the motion to check whether that motion is simple harmonic motion or not, right? So what we are going to discuss today is all about characteristics of simple harmonic motion, right? Simple harmonic motion. Now see, what's the first condition? As we have already discussed in the simple harmonic motion, it must be periodic, it must be oscillatory, right? It must be periodic or it must be oscillatory. So here our first condition is what? The motion must be oscillatory, right? Or you can say periodic, but here the good term would be oscillatory, right? Since it must be to and fro too. So motion should be oscillatory, right? What's the second condition of the simple harmonic motion? Some restoring force must act on the vibrating body. Some, initially let me write this point, then I'll explain you, right? Second is restoring force must act on the vibrating body, right? Now see what's this point says, some restoring force must act on the vibrating body. If I again take this example, mass spring system, so when I stretched this spring, now this body is on its extreme position. Now here the force which will act on this body to take this body to its original mean position, this force, we said this is spring force, right? But this force is what we call the restoring force, which is restoring the position of the body to its original position, right? So some restoring force must act on the vibrating body. If I do take example of this simple pendulum, if I take this bob, this is known as bob in this simple pendulum. When I take this bob here and I throw this bob from the extreme position, here would be some force acting on it to take this body to its original position, which means to its mean position. So that force we're gonna term that as restoring force. So some restoring force must act on the vibrating body. What's the third point? Let's read that. The third point is acceleration. This is very important, very main point to prove that whether the given motion, the particular motion is simple harmonic motion or not. So the acceleration of the body is directly proportional directly proportional to its negative displacement. Why this is negative displacement, I'll tell you the reason. No problem. Okay, so what this point says actually, that the acceleration of the body is directly proportional to its negative displacement, right? So this is the main point. In order to prove the given motion is harmonic motion, simple harmonic motion or not, is it SHM or not, right? So the acceleration of that body must be directly proportional to the negative displacement. Now why is it negative displacement? Since this acceleration will always be towards mean position, this would be always, right, towards mean position. And this displacement would always be away from the mean position. This point would be more clear to you when we're going to discuss the each example of the simple harmonic motion. In our course we have three main examples given in our syllabus. So the first example is uniform circular motion and simple harmonic motion, or you can say motion of projection of particle along a circular path, right? Second, we have elastic restoring force, motion under elastic restoring force, which we actually term as Hooke's law. And the third is simple point pendulum. So we're going to discuss or learn each and everything in very detail in this chapter. Away from the mean position, this would be away from the mean position. So now you can see the one is towards the mean position and another one is away from the mean position. So this negative sign actually shows the position, the direction, right? One is towards, one is away, right? And both are directly proportional, means if the acceleration would be increased, the negative displacement would be increased, right? Now we have the last point of the characteristics, and that point is total energy of the system would always remain conserved. Total, we'll prove this in simple pendulum, right? That how the total energy of the system remains conserved. In every motion of simple harmonic motion, the total energy remains, the total energy of the system remains conserved. Okay, so in today's video we have uh, discussed about characteristics of simple harmonic motion. If now you want to check a given motion is simple harmonic motion or not, you must apply these conditions to that motion in order to prove that that given motion is simple harmonic motion or not. By these points you'll easily gonna get that the given motion is simple harmonic motion or not. So this was all for today. In the next video we're gonna discuss motion of projection of particle along a circular path, or you can say uniform circular motion and simple harmonic motion, the connection between uniform circular motion and simple harmonic motion.